Welcome back, everyone. As a quick review, last class we talked about how most of the chemistry and energy transfer we encounter in our lives is determined by the interaction between electrons. So today we'll talk about how the spin of those electrons creates magnetism. There's a lot to cover, so pay attention and let me know if you have any questions. Antiferromagnetic materials also include metals like chromium, iron, and manganese. These materials have small positive magnetic susceptibilities, so they are only weakly attracted to external magnetic fields. At an atomic level, their electron spins appear similar to those of ferromagnets, but the magnetic moments align in a regular pattern with neighboring spins pointing in opposite directions. Ferromagnetic materials exhibit a long-range ordering phenomenon at the atomic level, which causes the unpaired electron spins to line up parallel with each other in a region called the domain. Magnets are usually made of a group of metals, such as nickel, cobalt, or iron, that are called the ferromagnetic metals. Ferromagnets have a maximum temperature where the magnetic ordering disappears as a result of thermal excitation. This temperature is called the Curie temperature. Magnets, 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 magnets. The needle of a compass is a permanent magnet while a paperclip is not. The paperclip only retains its poles while it is inside a magnetic field. So what are magnetism and antiferromagnetism? Magnetism is actually everywhere. All materials are made of atoms, and atoms have electrons, and every electron has a magnetic moment, and we call this a spin up or spin down. And in most materials, the amount of spin up and spin down electrons are equal on each atom, and you don't notice any magnetism in your daily life. The materials that you would think of as being magnetic are what we call ferromagnets, and if you were to zoom in on every atom in the material, they would have a small amount of more spin up than spin down electrons. And if you add them all up, you see a noticeable magnetic field, and that's why two magnets will stick to each other. They're trying to balance out their spins. And in antiferromagnets, on each atom, you still have a net spin, but the neighboring atoms cancel out each other's spin. And so antiferromagnets do not have the same attraction that you would think of with permanent magnets. If you zoom in on the atoms, this interaction is very strong, and we use that to manipulate magnetic moments when we store data.
My research project was under the lens of anti-ferromagnetic materials, and I worked with Daniel Shoemaker's group. Scientists will classify magnets in a very specific way depending on how the electrons are interacting, how the material interacts with the magnetic field, what happens to the material at certain temperatures.
So what does our lab do? Our lab does a lot of different things, but one of the things that we really enjoy is growing crystals. And when you think of crystals, you may think of rocks or gems. And what you may not know is that actually most metals are crystalline. And part of Carmen's project was building equipment so that we can grow single crystals of metals. And by understanding these materials, we can see how the magnetism allows them to become like little machines that manipulate spins in specific ways.
So what I was tasked with was to build a vertical Bridgman furnace, which is a very special type of furnace that creates a very specific heating profile. And what happens in this furnace is you get a very slow heating of the material, and then a very, very slow cooling of the material. And what that typically results in is something called a single crystal. During the summer of 2019, I was in Champaign during the week doing research on anti-ferromagnetic materials, and on the weekends I would drive to Chicago and I would tap dance with the company that I'm a part of. And I found myself thinking about electron spins and magnetic moments while I was in rehearsal, and I found myself in the lab tap dancing, while I was waiting for a sample to finish. And it just felt like an interesting challenge to try to communicate some of these physics concepts using tap dance. It felt like it would be fun, and it felt like it would be something that people might have not seen before and they might find inspiration from.
So was I surprised that research in our lab had led to Carmen choreographing a dance about it? I was pretty surprised. I knew that Carmen was a professional tap dancer, and that alone is not so surprising because so many scientists have a creative side that's really vibrant and part of their lives. But I was really excited to see where Carmen would make intersections between her dance and her research.
So generally we're looking at magnetism. So we get to see some imagery, a horseshoe magnet, the turning of a compass. But we also get to see, and something I'm very excited about showing, is what actually happens at an atomic level in a ferromagnet or an anti-ferromagnet. We get to see the contrast of those two things, and we get to see what happens when heat affects them. Heat is a catalyst for a lot of materials. And so we get to see these things as an audience member without that fancy microscope, without the years and years it takes of training to become a scientist. I also think that as a dancer, I've learned incredible discipline. I've learned to be very flexible. Improvisation is a huge cornerstone of what tap dance is all about. And I think that very much helps me when I look at scientific concepts and scientific problems. Both of these things require communication. They require an understanding of your audience, and I will tell you that they are incredibly intertwined.
Do I think of our research in terms of artistic expression? Absolutely. I think one important part of research and science in general is that you have to be able to communicate what you're doing. And we spend a lot of time thinking about how to communicate effectively, how to convey the message that we want to convey, and how to be clear about it. Another way that science is very much like art is that you get exciting things when you take two styles and you mash them together. You learn a lot of different techniques, talk to a lot of people, and you gain experience in a lot of different fields. And when you combine them together, you see opportunities that weren't there before.
My mom is a teacher and my dad is a metallurgist, which is just a material scientist who really loves metals. And so my entire life was filled with different types of creative projects and music and constant quizzing on my dad's periodic table. And so it was a natural progression for me to feel as if dance and science were equally a part of my life since the day I was born. I think that the creativity involved in dance and the creativity required in science are very similar, but they're just different ways of expressing that creativity.
What do I think is the impact of this dance? I think one thing that I like about it is that it shows people that science is everywhere and scientists are everywhere. I also really just am glad that Carmen enjoys it. I think taking two things in your life that are important to you and putting them together is really exciting.